Japan's a mountainous island nation hit by over 1,500 earthquakes every year, run high-speed transit with an average delay of less than 54 seconds per train. While major global powers spend billions battling cracked highways, delayed subways, and failing power grids, Japan quietly turned extreme precision into a daily way of life. Decades of relentless technical refinement transformed an overcrowded archipelago into a living blueprint for the future that leaves international engineers stunned. Operating since 1964, the high-speed Shinkansen network has transported over 10 billion passengers with zero fatal derailment or collision accidents. Modern bullet trains run at standard operational speeds of 320 kilometers per hour, while keeping the average system-wide delay below 54 seconds per train annually. Moving over 400 million annual commuters, the transit operator schedules departures on razor-sharp, multi-second tracking grids. Any train arriving 60 seconds behind schedule triggers an official written delay certificate for commuters to show their employers. This extreme level of mathematical consistency keeps the entire national economy moving without transit friction. The Tokyo subway network links 13 subterranean lines and 285 stations to carry more than 9 million daily passengers across the city. Peak morning departures run every 80 seconds on major platforms without creating congestion or dangerous track backups. Platform attendants known as Oshiya wear white gloves to gently pack late boarders into train cars to avoid minor 30-second departures delays. The entire high-density underground grid maintains an on-time reliability score exceeding 99% each working week. This mechanical precision proves that massive population density does not have to create transit chaos. Completed in 1998 across the turbulent Akashi Strait, the Akashi Kaikyo Bridge features a record-breaking central span of 1,991 meters. Two massive suspension cables contain 36,830 high-strength steel wires twisted together to resist intense ocean weather. During construction, the violent magnitude 7.2 Kobe earthquake shoved the main towers 1 meter further apart without cracking the submerged foundation caissons. Engineers recalculated the cable math on site and completed the bridge to survive 280 kilometers per hour typhoon winds and 4.5 meters per second ocean currents. Facing roughly 20% of the world's major earthquakes, Japanese engineers build high-rises on flexible base isolation bearings made of steel and synthetic rubber. These thick foundation pads decouple structures from bedrock, cutting horizontal ground acceleration by up to 75%. The 634-meter Tokyo Skytree relies on a massive internal concrete shaft weighing 11,000 metric tons to act as a dynamic counterweight. When tremors push the outer frame, the central pillar sways in the opposite direction, modernizing a principle used in wooden pagodas for 1,400 years. Built inside Osaka Bay on an artificial island spanning 511 hectares, Kansai International Airport required moving 180 million cubic meters of earth. Because the soft ocean floor caused the land to sink by over 3.8 meters, engineers designed the entire facility around continuous mechanical leveling. The 1.7-kilometer passenger terminal rests on 900 steel support columns, fitted with high-tonnage hydraulic jacks and electronic tilt sensors. Whenever a floor section sinks by a few millimeters, technicians insert steel plates beneath the columns, keeping flight operations smooth. Inside the automated facilities of Fanuc, robotic arms build new industrial machinery in complete darkness with zero interior heating. These lights-out manufacturing facilities operate continuously for 30 consecutive days without any humans present on the factory floor. The automated tools navigate with microscopic laser precision, supporting a national density of roughly 390 industrial robots per 10,000 human factory workers. Human technicians only visit during scheduled maintenance windows to check diagnostic software and replace worn drill tooling. Japanese industries have integrated mechanical assistance into daily public tasks since the early 1980s. Hospital carts automatically deliver medicine across multiple facility floors, while robotic hotel desks process international check-ins in under 45 seconds. Casual restaurants use wheeled robotic servers that deliver meals with a 99.8% accuracy rate, cutting order mistakes and food waste. Backed by 40 years of continuous research, Japanese society treats automated machines as dependable daily tools rather than economic threats. The Seikan Tunnel connects Honshu to Hokkaido through 24 years of continuous subsea construction under extreme water pressure. The completed rail passage stretches across 53.85 kilometers, with 23.3 kilometers running 100 meters below the seabed. Drilling teams survived multiple emergency breaches where ocean water flooded work zones at 11 tons per minute, inventing high-pressure chemical grouting to seal the rock walls. Today, high-speed bullet trains cross through this undersea corridor at 260 kilometers per hour with complete passenger safety. Located 50 meters below ground, the metropolitan area outer underground discharge channel shields Tokyo's 37 million residents from seasonal typhoons. The system gathers floodwaters into 5 giant silos, measuring 65 meters tall, channeling runoff into a massive tank supported by 59 concrete pillars. Converted aircraft gas turbines pump water out to sea at 200 cubic meters per second, slashing regional flood damage by 90%. This subterranean engineering marvel prevents billion-dollar flood disasters without most residents ever knowing it activated. Every high-end smartphone, artificial intelligence cluster, and supercomputer on Earth depends entirely on an invisible manufacturing bottleneck controlled by Japan. While global headlines focus on chip designers like NVIDIA and foundries like TSMC, the multi-million-dollar extreme ultraviolet lithography systems that print microscopic circuits rely on specialized sub-nanometer optical components and synthetic mirrors polished by Japanese legacy firms. These precision optics must guide light wavelengths so minuscule that even a surface imperfection, the width of a single atom, can distort the pattern and ruin an entire silicon wafer. This level of extreme manufacturing discipline is rooted in the philosophy of Monozukuri, where the pursuit of mechanical perfection is treated not merely as industrial mass production, but as a dedicated craft refined through decades of continuous microscopic iterations. Beyond optical lenses, specialized Japanese chemical firms quietly control over 70% of the global market share for essential semiconductor raw materials, including ultra-pure chemical photoresists, silicon wafers, and specialized fluorinated etching gases. Producing these specialized chemicals requires purity levels exceeding 99.9999999%, creating a technical barrier to entry that foreign competitors with billions in capital still struggle to replicate at scale. Because advanced chip foundries across the United States, Taiwan, and South Korea cannot etch a single 3-nanometer transistor. Without these exact formulations, the entire global hardware ecosystem rests on this narrow supply line. If this silent pipeline of Japanese precision optics and ultra-pure chemical materials were cut off, modern microchip production worldwide would grind to a complete halt within months. Across the country, roughly 60,000 convenience stores deliver essential public services to a population of 125 million people. These neighborhood shops process utility bills, handle local taxes, ship luggage, and restock fresh bento boxes 3 times every day. During major earthquakes and weather emergencies, convenience networks are legally designated as official disaster relief hubs that supply emergency food and drinking water. Advanced logistics algorithms track local weather and foot traffic to restock critical supplies before store shelves ever run out. With only 15% of its mountainous terrain suitable for development, Japan overcame severe natural constraints through strict technical discipline. Applying the continuous improvement philosophy of Kaizen, industries systematically eliminated operational waste and design flaws for over 70 years. This relentless cultural focus on reliability created bullet trains that never derail, skyscrapers that neutralize earthquakes, and dark automated factories. Living in the future came down to a simple national decision: building essential infrastructure to a standard of zero failure. If this video was helpful, like, share, and subscribe for more content.